It is part 2 of section 30.1, derivative and differentiation rules. In the first part of the section, you learn to calculate average slopes for various interval length h and estimated the instantaneous slope by letting h approach 0. Here we summarize to define the derivative of a function. Here we first formulate the difference quotient and take a limit. Once the limit exists, then we will call it the derivative of the function f. And we'll try to use the notation f prime or df over dx at x. Let's see this example. Use the definition to find the derivatives of the functions. That means we first find the difference quotient and simplify it, and then apply the limit. Okay, let's see part A. Okay, for this one, now f of x plus h minus f of x over h. Okay, that is same as x plus h, because f of x is x. It is same as x plus h and minus, and f of x is same as x divided by h. Now this x, that x will be cancelled, and remaining part is h and over h, which is 1. For every h is 1, so if you are taking limit, then the value must be 1, which means that, and for this function, f of x is x, the derivative is always 1 for every x, right? Okay, now you can do this one yourself. Now we'll go to part C. Okay, for this one, now f of x plus h minus f of x over h. Okay, that is same as, now here x plus h cubed. Okay, so x plus h cubed minus x cubed over h. Now that is same as, okay, we expanded this term, then x cubed plus 3x squared h plus 3xh squared and plus h cubed and minus x cubed and divided by h. We can cancel this and this, and here divided by h, but here we have h terms, h for each term, so we can cancel h. Okay, that is now 3x squared plus 3xh and plus h squared. Now that is the simplified terms. Okay, now we are taking limit. Okay, here limit h approaches 0. Then from this one will remain unchanged, but that one will go to 0. And again, this one will approach 0. So that we have 3x squared. Okay, that's the limit, which means that here, from this one, we can say x cubed derivative is same as 3x squared, right? Okay. For this one, if you do the same, then we'll see the derivative of x squared will be 2x. Here we write down the results. For x, its derivative is 1, we found here. For x squared, its derivative is 2x. And here we have x cubed, its derivative is 3x squared. In general, by using this technique, you can find here this formula for x to the n. Its derivative is n times x to the n minus 1. Here x cubed, 3 will go out, and 3 is changed to 2 here, right? So in this way, you can find the formula. But here, n doesn't have to be integer. In general, for every real number, non-zero real number, you can use this formula. Let's see this example. Now, we differentiate the following powers of f. Okay, once x to the 6, then, okay, x to the 6 derivative is same as 6 will go out, and then x to the 5. Okay, for that one, if we apply the derivative, okay, derivative of that one will be 3 over 2 will go out, and then x, and this power minus 1, which means 1 over 2. Okay, for this one, now if we try to get derivative, then half will go out, and then here x to the half minus 1, so minus 1 over 2. Okay, let's try to rewrite this one. X to the minus half is 1 over square root of x, so that we can rewrite this one, 1 over 2 square root of x. Of course, when x is negative, it is not defined. Also the same for this one. Okay. Now, we expanded the definition of the derivative for various functions. And here, these are just x to the sum power. And for x to the power n, we can get such a formula. Now, we'll try to apply the definition of derivative for various functions by using here some extra differentiation rules. Okay, let's start with a function given as a linear combination of two functions, a times u of x plus b times v of x, and a, b are constants. Then here we are using the quotient. Then at x plus h, we can write in this way, and at x we have that divided by h. Now we rearrange it. Then here for a, we have this term minus that one here, and for quotient b, we have now top is v x plus h minus, along with that one, minus b vx, and we have h over there. Now once h approaches 0, then assuming that the limit exists, that will approach to u derivative, u prime, that will also approach v prime, assuming limit exists. So we can have this formula. The linear combination of two functions its derivative is basically just the linear combination of the derivatives of each function. So in a sense, here derivative is a kind of a linear operator. if you are in linear algebra, then you can understand this. Of course, later on in chapter 4, we'll deal with linear algebra. Okay. Now, let f is given as here, product of two functions. Then, by using again the definition, and we start with this difference quotient, then that is now, okay, at x plus h, we have this term, and at x, we have that one. Now, we try to subtract this term to the numerator and add this term. So these two are the same, and we separate it out. For these first two terms, we have v x plus h, and we can go out, we can put it here. And for the last two terms, now ux is common, so we put here. And assuming that the derivative exists, that means here limit exists as h approaches 0, then here this term will approach to here u prime, and this term will approach v prime, so that if we apply limit h approaches 0, then these two terms will converge to u prime v plus u v prime. So here we have a formula. The derivative of the product can be obtained by using this. 1 each time is differentiated, and here the multiples are added. That's the formula. Okay. Let's try to get derivative of this function. Now we'll try to check yet the product rule. Okay. If you try to get derivative for x to the 6 directly, then from this one we have now 6 times x to the 5. Now x to the 6 can be written as x squared and times x to the 4. Now two functions are multiplied, so by using product rule we may try to get the derivative. Okay, from this one, now we differentiate first term, which is 2x and x to the 4. Now plus, and first term the same. Now derivative of second term, that is 4x cubed. Okay, from here that is 2x to the 5 from the first one. And second one, that is 4x to the 5. So here we have 6x to the 5. This term, this result, and that result are the same. Okay. Now, thus the curve y equals x to the 4 minus 2x squared plus 2 have any horizontal tangent line. Use the information you just found to sketch the graph. Okay. Here, horizontal tangent line means that at the point, the slope must be 0, right? And that is, derivative must be 0. So we start with y prime, the derivative of y with respect to x, which is same as 4x cubed from this one, and minus 2 times 2, so that 4x, and the constant term, okay, slope of the constant, and that is horizontal. If you consider this one only, then if you try to get y equal to the graph of that, then that one will be here, that is 2, and that is horizontal. So slope of this function at every point must be 0. So derivative of the constant must be 0. Okay. Okay. So we reach the derivative of a given function, and we have to find the point where the slope is 0. So let's say equals 0. Then from this one, now 4x are common, and then that is x squared minus 1 equals 0. So we have here 4 times x times and x plus 1, x minus 1 equal 0, which means that when x equal 0 or 1 or minus 1, then the tangent line must be horizontal. That is the same as just the derivative is 0. Okay, now we'll use this information to sketch the graph. Okay, when you try to sketch the graph, you learned from high school that, and try to find the intercepts, x-intercept and y-intercept, and any other information so that you can get a better graph here. Now, let's try to use the information. Okay, here now. Okay, once x equals 0, then there is 2. So that it will pass that on. And then here, slope will be 0 at 0 and 1 and minus 1. But once x equals 0, then y value must be here. Okay, once x equals 0, then y value must be 2. You can quite easily get y value from this equation. Once x equals 1, then 1 minus 2 plus 2. So that here there will be 1. And also, when x is minus 1, the same value, which is 1. So that once minus 1, then the height, okay, height must be here 1. I should start with this one much higher. Okay, let's try to change that here. That is 2, and this is now 1. Okay, okay. When it's okay, minus 1, then height is 1. It is passing this point, of course, passing this one, and it's 1, then passing that on. And passing, and at these 3 points, the curve must be horizontal, which means that, and here, okay, that is passing this way. And then now here the slope must be 0, so it is start coming up, and same over there coming up like that. In fact, the graph of this function must be symmetric with respect to y-axis. So we have such graph, the shape of W, that's the graph. And we can sketch the graph by using the information we obtained from derivative. Okay, so if you are using derivative, the results, then you can get very good graph. And many cases, people are using also second derivative information to get a better graph, but we'll not go to details of such graphing techniques. Okay. Now, consider a computer program in MathTalent. Now, here we do some symbolic computation, and try to get a derivative by using the definition. First, for given function, we formulate the difference quotient and take a limit as h approaches 0, but this result will be a little bit messy, and we simplify. And we did, in fact, and earlier when we are using the definition to find the derivative, and at some point we try to simplify the formula, so exactly the same way we do in programming. So we choose some various symbolic functions here. Now that is only xn, but I implemented here a linear combination of two functions, and product and quotient, and that is a composite. And I use this program to find the derivative, and these are results. And out of these results, we can get here mathematical formula xn prime derivative as n times x to the n minus 1. That is power rule already we learned, and that is now here. Okay, that is a u prime plus b v prime. So that's exactly this one. That is a linearity rule. And for product, and we got this result, and so that it means this one. There is a product rule. For quotient, here that can be written mathematically in this way. Here u over v derivative is same as, now the numerator is u prime v minus u v prime, and denominator is v squared, which is called the quotient rule. And for composite function, here that will be same as u prime v times v prime, that is chain rule. And of course, by using the definition, I here try to get the result by using definition. Just start with the quotient and take a limit and simplify. So if you do the computation, then you will get exactly the same result. And here, earlier also, we try to get those results, but just only these two cases, but for other cases, you can get exactly the same result. Okay. Okay. Now we'll try to find the derivative of g of x is defined in this way. This is now, if you expand, then is 10th order polynomial, so that you may get derivative by using here power rule. However, if you try to do that, then it's way complicated. So we may consider this given function as a composite function, and u of x is x to the 10. Now, momentarily, we consider this term as a variable, and then v of x is now the variable 2x plus 1. With this definition, the given function g of x is the same as u of v of x. Now, if we are using the chain rule, then u of x, okay, u of x derivative is 10 x to the 9, and here derivative of v is 2. So that now g prime x is u prime, but you have to get the value at v of x, so that here u prime v of x v prime x. Rather than x, you have to put here v of x, so that 10 times now, okay, rather than x, we are using v of x to the 9, and v prime is 2. Now this one is here 2x plus 1, and we multiply this 2, and that will be 20, and v of x is same as 2x plus 1, so that we reach this term. So that's the final answer. Okay, it seems quite complicated, but you can think in this way. Momentarily, if you try to get from this one, if you try to get derivative with respect to x, then momentarily you think this one as a variable. Then there will be 10. Now this variable and plus 1 and power 9. And then you think here derivative of this variable with respect to x. Then there will be 2. That's the result. This is same as this one. So this chain rule can be considered in this way. Okay. Another way is, okay, now g of x is same as here u v of x. Okay. Okay. Now g prime x, if we try to write down this one in quotient form, then that is called dg over dx. Now for this one, and of course, because it's u, it's the same. In fact, now du over dx, you can write in this way, because apparently now there is a u over there. Okay, now for that one, you may think here du over dv, like you deal with this one like a quotient. So that, and you put over there to make it the same, left hand side, right hand side. Now we put here now dv to numerator, and here now dx. This portion is the same as here the given function here differentiated with respect to v. That is same as, along with this variable, we consider this one as a variable, v here, a variable, and differentiate. That portion is exactly same as that one. Now v derivative with respect to x is now 2 over there. So the chain rule can be considered in this way, so that is quite reasonable. Okay. Okay, here we again now algebraic derivation for derivatives. Here, first of all, we say power rule holds for real number n, not necessarily integer. Just for a real number, we can use it. For quotient rule, here there is a mathematical derivation u over v prime, and that is another way of getting quotient rule, and that is rather than u over v, we write down as product u v to the minus 1, power minus 1, and we are using here product rule. And then here we simplify, and we can get it. So in a sense, quotient rule is a special form of the product rule. Now for chain rule, we can verify algebraically in this way. Here, now by definition, we have this one, and we are here, okay, here we are trying to put here this term and that term, and so that if you try to cancel, then it'll become that one. So it's the same. And for each one, we try to take a limit, and we can get such one. So this algebraic manipulation is basically now here the same as that one. Just we deal with this derivative like as a quotient, and then here try to multiply dv in both sides, and then try to take a derivative in this one, that one separately, and multiply them, right? So exactly same idea. Okay. Okay, here we may rewrite this equation in this form. Okay, that is here. Okay, is a limit delta x approaches 0, and the same as change in u divided by change in x. Now that can be written here, change in v is multiplied in the bottom and multiplied in the top. So each one is now has a limit, and in this way, so that we can get the final result. So eventually, the chain rule looks like we are dealing with the quotients and derivative, but we consider the derivative as just quotient, and then we can get it. But a derivative, once you write in this way, then it's not quotient, rigorously speaking, but you may deal with it that way, because anyway, the derivative is limit of the quotient, so that even though you consider the derivative as a quotient, it's okay. Okay. Okay, for this one, you can get derivative quite easily. Now, by using product rule, you have to get first this derivative times this one, and this term times derivative of that one. But when you try to get derivative for that one, you have to use again the chain rule, right? And so that you can get the derivative quite easily. Okay, do it yourself. Okay, that's the end of section. Thank you.